Hello, my name is Eric Georgin. I am involved in the GRP BioFmet dedicated to new metrological methods for biofuel materials analysis. Today, I will be delivering a presentation on the fundamentals of humidity and moisture measurement, with a focus on the principles of moisture measurement. As an introduction, I would like to remind you of the types of challenges that we face when measuring moisture in solid materials. The first one relies on the fact that moisture content is not uniformly distributed throughout a material. The second one concerns the difference between moisture content and water content. Moisture content refers to the total amount of water in a material, including any volatile organic compounds, also known as VOCs, whereas water content only refers to the total amount of water present in a material. The last one corresponds to the various degrees of water binding to the solid matrix. Water can bind to a solid material in multiple ways, corresponding to different types of interaction. In a solid matrix, we can distinguish between several types of water, including free water, capillary water, physically bound water, and chemically bound water. As it has been mentioned in the previous slide, water can form different types of bonds with other molecules or surfaces, depending on the conditions and properties of the solid matrix. Free water, for example, this type of water is not bound to the solid matrix and can be easily removed from it. Among the physically bound water, we can distinguish capillary water. This type of water is held by capillary forces, which are relatively weak and can be overcome by gravity or other external forces. Physically bound water. This type of water is bound to the solid matrix through physical forces, such as van der Waals forces or hydrogen bonds. These forces are stronger than capillary forces, but weaker than chemical bonds. Chemical bound water. This type of water is bound to the solid matrix through chemical bonds, such as covalent bonds or ionic bonds. These bonds are the strongest type of bond and require significant energy to break. We may also identify this type of bond as the water of crystallization, for example, in hydrates or solvates. The strength of the bond increases from free water to chemically bound water, depending on the type of bond formed. Water can affect many thermophysical properties, including length, conductivity, weight, electrical impedance, color, refractive index, or thermal conductivity. Water also has the ability to absorb infrared radiation, ultraviolet radiation, or microwave radiation. Therefore, there are many different measurement principles used to determine either the moisture content or the water content of a material. In metrology, direct measurement techniques refer to methods that enable the measurement of the measurand of interest without any intermediate quantities. This means that the physical quantity being measured is obtained directly from a calibrated measurement instrument or sensor without the need for any additional steps. Direct measurement techniques are considered the most accurate and precise way of determining the value of a physical quantity and are often used to directly realize or define the primary unit of measurement for that quantity. It implies the use of reference or absolute measurement techniques. The most widespread direct or reference measurement techniques are the following: thermogravimetry, which measure the weight loss of a sample due to the evaporation of moisture. Another popular approach is the loss and drying method, which determines the moisture content of a sample by heating it in an oven and measuring the weight loss. Gain on weighting, on the other hand, involves measuring the weight gain of a sample after it absorbs moisture from the atmosphere. Thermogravimetric analysis is a sophisticated technique that measures the weight change of a sample under controlled temperature and atmosphere conditions. Chemical analysis techniques such as Karl-Fischer titration, which uses volumetric or coulometric methods, are commonly used to measure water content in samples with low moisture levels. Electrolysis of water combined with pentoxide phosphorus is another chemical analysis technique used to determine the water content of a sample. Evolved water measurement techniques involve using an oven and carrier gas to evaporate and collect the moisture from a sample. This technique is often combined with chemical analysis. Then, in metrology, indirect measurement techniques are used to measure a physical quantity of interest by measuring another property that is affected or sensitive to it. This means that the measurand being measured needs to be calibrated using reference or absolute measurement techniques. Indirect measurement techniques typically produce an electrical or other output on an arbitrary scale that can only be related to the measurand through calibration. Examples of measurement techniques include electrical conductance, electrical capacitance, microwave resonance, and near-infrared reflection. Overall, indirect measurement techniques are useful for measuring physical quantities that are difficult or impossible to measure directly, and they play an important role in many fields of science and engineering. Among the different families of indirect or secondary method, various electromagnetic techniques can be used for moisture measurement, including those that utilize electrical resistance or conductance, electrical capacitance, dielectric permittivity, microwaves, radio frequencies, and time domain reflectometry. In addition to electromagnetic techniques, thermal methods such as near-infrared or dual-needle heat pulse can be used for moisture measurement, as well as nuclear techniques such as nuclear magnetic resonance and gamma attenuation. As we have seen, there are many instruments and measurement techniques available for determining various physical quantities related to moisture. The choice of measurement technique can impact which measurand, that is to say, physical quantity, is accessible for measurement. For example, consider the measurement technique known as loss on drying. In this technique, the measurand being measured is moisture content, which refers to the total amount of water in material, including any volatile organic compounds. This measurement technique will represent the total amount of moisture in the material. Depending on the context, moisture content can be expressed on a dry basis, that is to say, as a percentage of the material's dry weight, or on a wet basis, that is to say, as a percentage of the material's weight wet. Both quantities, whether expressed on a dry basis or wet basis, can be related to each other using the equation presented in the slide. Another interesting example of physical quantities in the food industry is the water activity and equilibrium relative humidity, ERH. Water activity represents the ratio between the water vapor pressure of a material to the water vapor pressure of pure water under the same condition. On the other hand, ERH is the value of relative humidity of the air at which there is no net exchange of moisture with any nearby substance. Water activity is often measured as ERH in certain cases where water activity may represent the free water in the material being studied. By using a sorption isotherm curve, it is possible to establish a relationship between water activity and moisture content on a dry basis. In conclusion, moisture measurement is a complex topic that encompasses various aspects, such as the measurand of interest, the measurement technique, and the form of water bonding, among others. The way in which results are expressed also plays a crucial role. I hope you found this introduction to the fundamentals of moisture measurement informative and interesting. And thank you very much for your attention.